Hello everyone, I am Mavroudi and I'm a PhD student at Johns Hopkins University. In this video I will be presenting our work introducing actor-centric tubelets for real-time activity detection in extended videos. This is joint work with Prashast Vidal and my advisor Rene Vidal. The problem we are trying to solve is to temporally detect activities of humans and vehicles in long untrimmed surveillance videos. As you can see, extended videos typically contain multiple actors performing multiple activities in different regions of indoor or outdoor scenes. This type of videos are particularly challenging to understand because of the large variation in the duration and scale of activities. For example, activities can be very short, such as closing a vehicle door, or very long, such as riding a bike. Also, they can occur in the foreground or in the background. Another challenge is the large variation in the type of activities, which can involve one actor, or multiple actors, or actor-object interactions. Furthermore, extended videos typically contain multiple co-occurring activities. All these unique characteristics of extended videos cause current state-of-the-art global CNNs, such as the RC3D, to fail in detecting activities in them. This is the reason why existing approaches for activity detection in extended videos first narrow down the visual search space by identifying video subvolumes that might contain activities. Early works were either assuming known spatial localization or were leveraging object detection and background subtraction for localization. Then, they were recognizing activities by modeling actor-object interactions. However, they were limited to a single type of activities, namely person-vehicle interactions, and were leveraging handcrafted bag of visual words representations. Recent works leverage deep models to identify video subvolumes in the form of cuboids or action tubes. Then they detect activities in those using powerful CNN models. However, these approaches do not model the long-term history of an actor's activities or actor-object interactions. Instead, we propose a framework for activity detection in extended videos, which captures long-range spatio-temporal context via actor-centric tubelets and exploits rich visual actor-object interactions via graph neural networks. So here is a more detailed overview of the proposed complex activity detection framework. Starting from an input video, we extract actor-centric tubelets of interest. These are tubelets of varied length that are associated with a tracklet of one primary actor, shown in green, and ideally contain all visual context that is relevant to that actor. We then feed each one of those tubelets to our activity detection module in order to recognize the activities that are being performed by the primary actor of the tublet over time. Our action recognition module is designed to capture actor-object interactions and temporal dynamics. Finally, we aggregate the action detections from each tublet to obtain action detections for the original extended video. Our tubelet extraction method starts by detecting actors, people, and vehicles using an off-the-shelf object detector trained on an external image dataset. Then these detections are tracked with an off-the-shelf tracker to help add temporal context and fill in missing actor detections. The resulting tracks, however, might be of non-interesting actors, such as stationary cars, and they do not have rich spatial context. This is why we also find actor-centric regions of interest per frame. These regions capture different types of activities, such as human-vehicle interactions, and each one of them is associated with the primary actor. They are obtained by associating actor detections by leveraging domain knowledge summarized in simple handcrafted rules, which are based on normalized distance and motion thresholds. Given these regions, we first compute the union box of all frame regions of interest associated with a particular primary actor. Afterwards, we link the primary actor regions of interest using actor tracks to obtain tubelets. Our tubelets, after some further post-processing to ensure smoothness and constant height and width, look like this. Given the extracted tubelets, we are now ready to detect activities in each one of them. To do this, we predict multiple action labels per frame for the primary actor of each tublet. A straightforward way to approach these types of problems is to localize the actor, extract local features, and then use these features to predict their actions. However, this approach ignores spatio-temporal interactions. In this work, we model such interactions with a spatio-temporal graph and perform representation learning on it in order to yield context-aware actor embeddings. To see why visual relationships are a powerful cue and illustrate our visual graph, we can see in this example that in this frame it is hard to tell what the person is doing by just looking at the local person feature. However, the information about surrounding objects and their position can help us recognize the action transport heavy carry. Further, looking at the change of the pose of the actor from a previous time step can help us recognize the action unloading. All these types of interactions can be encoded in a visual spatio-temporal graph which has directed edges, different node and edge types, node attributes corresponding to local features, and edge attributes. Given the detection-based visual graph, we use a graph neural network to obtain context-aware actor features. Graph neural networks are deep neural networks that can operate directly on graphs and result in graph structure-aware node embeddings by learning how to iteratively aggregate features from neighbors. In particular, we chose the recently published ST-MPNN that enables representation learning on spatio-temporal, heterogeneous visual graphs, and which iteratively refines the visual graph connectivity with attention mechanisms, supports various node and edge types, and utilizes edge features. Here is how we utilize the ST-MPNN for processing our tubelets. We start from an optical flow tublet and divide it into non-overlapping 2-second chunks. We then pass each chunk through a pre-trained 3D convolutional network and pull actor and object features based on detections in order to build the visual graph. We pass this graph through our ST-MPNN and obtain context-aware actor embeddings. We feed those embeddings to action classifiers, and the output is a set of scores for each activity in each chunk. The ST-MPNN and action classifiers are jointly trained with a weighted binary cross-entropy loss to tackle the class imbalance. The final post-processing step of our pipeline converts the time series of scores for each action class to action detections with start and frames and confidence scores by finding local maxima and extending them in time based on a relative score threshold. Alternatively, we can output detections of a fixed duration by extending the detection by one chunk to the left and one to the right. For our experiments, we train only the ST-MPNN and action classifiers given actor-level annotations of 784 videos from the MEVA dataset. We then evaluate the model on our internal MEVA validation set and the external sequestered dataset leaderboard. Metrics are related to the probability of missing a detection at various time-based false alarm rates, so lower metrics indicate a better performance. Our system exploits parallel processing to analyze videos in 0.97 real time and results in around 48% AUDC at 0.2 TFA. On the one hand, our system lags behind other systems submitted on the leaderboard, which potentially utilize end-to-end training and model ensembles. On the other hand, we see that our model performs competitively for most activity classes, being only significantly worse for classes for which we used very few training examples, such as person interacts with laptop or hand interacts with person. Qualitative results on the MEVA internal validation set show how our model can detect activities on an actor level in indoor scenes. False positives tend to have smaller scores. In this example, we see detections of the activity person enters through structure. In this example, we see detections for the activity person opens vehicle door in an outdoor scene. Our system can also detect activities both in the foreground and the background. However, occlusions and crowded scenes can result in missed actor detections, and that's missed activity detections. If we look at the tublet activity recall at 30 consecutive frames on the MEVA internal validation set, our tubelets are able to retrieve 68% of the ground truth activity instances. In summary, we presented a structured model for activity detection in extended videos, which models actor-object interactions, localizes activities on an actor level, can process videos in real time, and can be trained efficiently. Limitations of our current system are that it cannot be trained end-to-end and that it struggles with crowded scenes, which cause both missed activities and increased computational time. Thank you.